Hi, everyone. My name is Melvyn and I'm an associate professor at the University of Cambridge. And I'll be teaching a module on causal machine learning as part of Timberlake's summer school, which will be held at Churchill College, um, University of Cambridge. What I want to do in this very short introduction is to just give you a sense of what we will cover, the way that we will cover it, how you might think about the material in terms of points of departure, and just some general information that will hopefully give you help you make your decision in terms of whether you'd like to join the course. So first of all, the material that I will cover is a cut down version of a core course, which now features in the new MPhil program in the Faculty of Economics. It's a new degree in economics and data science, and the module causal machine learning is a core module, and I will be effectively teaching that and giving you the basics of that material in 2.5 days. So what we will cover really sits at the intersection of a number of literatures: machine learning, statistics, and econometrics. And we cover a mix of theory and applications. We might think of this as three main literatures. One is causal estimation and inference. And in that sense, we are largely sort of borrowing the methods and material from standard parametric methods that many of you may be familiar with. Where we depart from the parametric methods is where we prefer to be agnostic in terms of functional form choices. And so therefore we utilize high dimensional statistics for managing a bias variance trade-off. Essentially, in a simple way, we might have more information in terms of variables than the data might entertain reasonably. And so we need to make some selections, some variable selections. We're not going to do that in a data mining sense. We're going to do what might be called principled and modern data mining, which you will learn about on the course. The other literature is machine learning. So we know a lot about machine learning in terms of its performance in prediction problems. We will utilize exactly those prediction problems or prediction algorithms as part of our causal estimation and inference. And you will see quite clearly that the sort of architecture of these causal machine learning models depends critically on a number of machine learning prediction problems. So this whole vernacular, as you've probably seen if you have any exposure to econometrics, can be quite confusing. You hear sort of basic terms of machine learning methods for prediction, causal, and classification. You've seen reference to double robust methods in a parametric setting. You've perhaps heard about double debiased lasso, which represents a sort of machine learning linear departure from parametric methods. And then there's associated techniques around orthogonalization, the Frisch-Wall-Lovell theorem, sample splitting, honest estimation, and generalized random forest. Now, all of that together just seems something that's going to be very difficult to navigate. But we will take this in terms of small steps. We will, as much as possible, we'll focus on the intuition, and I think all will become clear. The way that we set this up is really in terms of points of departure. So one might think of a number of points of departure which we focus on. The first part is the part that's taught by Jeff. So Jeff's going to come in before me for 2.5 days and basically lend his considered experience in developing and teaching parametric methods, and he's going to cover a number of core identification strategies, including IV and difference in difference. So Jeff will be doing that, but when I sort of take over from Jeff, I'll be still focusing initially on the conditional expectation function and the linear approximation to that, and the associated ordinary least squares estimator is going to be a core a core platform that on which that we will start considering different non-parametric alternatives. So we'll be looking at high dimensional methods in statistics, principally looking at lasso for prediction, lasso, sort of double lasso rather, for causal inference, utilizing that alongside the Frisch-Wall-Lovell theorem, which basically is, in its simplest form, allows you to estimate a multivariate regression in a bivariate form. And that fundamental theorem in statistics is going to be critical in the way in which we develop and estimate methods for more advanced machine learning methods. So we won't just jump into non-parametric methods. We will go back right to the basics, and, for example, consider simple histograms, simple nearest neighbor methods, and consider those as discontinuous estimators. If you have a histogram and you're at the boundary of one bin and another, then the actual estimate of or the prediction of y, or whatever you are interested in prediction, will be very different according to where you are in terms of the boundary of the bin. So we'd like to smooth that estimator, and smoothing that estimator, we get the kernel estimators, and the kernel estimators can start to be, we will see how they provide a platform for thinking about more advanced machine learning methods, such as random forests and generalized random forests. The methods that we will look at treatment effects, and again, you will have already been exposed to the methodology and the platforms for thinking about treatment effects that Jeff will have developed. So we will then utilize that framework when we start thinking of estimating treatment effects in with machine learning methods. So we've got many applications that I will look at. Time of use electricity pricing, impact of institutions on growth, the impact of training on firm performance. We'll look at some applications in finance. So it covers a whole range of different methods. I think, what are we aiming at here? What's the sort of characteristics of potential participants? They range, I think, from you're just curious, you might understand econometrics and parametric methods, but more and more we start hearing about machine learning. At the same time, you may have a considerable exposure in parametric methods for parametric methods, but now you want to actually develop that understanding with the use of machine learning. You could also be a policymaker, and gradually policymakers, decision makers, that could be with could be within finance, there could be policy makers and decision makers in regulated industries, in financial sectors. And again, you may be utilizing treatment effect type estimators to make and evaluate the impact of various policies. And again, you'd like to see the extent to which machine learning can further develop understanding and perhaps utilize agnostic methods. So that's the basic sort of introduction. The course is going to be taught in I wouldn't say informal manner, but we will be emphasizing intuition and understanding. We're not just going to be throwing up loads of equations. The approach will be different. The slides will be rigorous. The slides will give you that deeper understanding, but much of the material will be presented in an informal, discursive fashion. You will take away from the course a wide range of an appreciation for a wide range of issues and case studies in machine learning for decision making, how these tools can be deployed in your area or sectors that you're interested in. I think the other point that I'd like to sort of end this short introduction is that I won't be presenting this as these methods are something that you must use. These methods will always be superior to their parametric alternatives. The framework that we will be using is, in one sense, do they provide a robust check on the parametric, more parsimonious method? So we will be taking a considered view of alternative ways of conducting causal inference across a number of applications and giving you enough information that you can critically evaluate the performance and understanding of these new causal machine learning tools. So I hope to see you in Churchill College in July, and until then, goodbye.